Broadcasting from Washington, D.C., this is Insider's Guide to Energy.
Welcome to Insider's Guide to Energy. I'm your host, Chris Sass, and with me is my co-host, Jeff McAulay. We're going to do another episode on batteries. Batteries are an exciting technology for me, Jeff. I'm looking forward to getting to this because, if we're going to hit this electrification goal, we need a lot of batteries. And watching the technology evolve is something that I've been anxious to see. And this company, I think, promises some different story or different technology. Jeff, welcome to the program.
Yeah, really excited to be here as always. And with us today is John Busbee, CEO of Xerion Advanced Battery Corporation. John, welcome to the show. Tell us a little bit about Xerion as we jump in.
So Xerion, we've been around since 2011, and basically we've come up with a new way to create the manufacturing of batteries through electroplating, kind of in toto. So.
Really, really fascinating. Looking forward to getting into this. So first of all, you've been in stealth mode for over a decade. So tell us a little bit about how this got started and the reason for keeping it under wraps for that period of time.
Well, and we weren't trying to hide anything. It was just that when we first got started, I was in the Air Force Research Labs. I was the program manager of nanotechnology. And, I'd seen how much hype could really impact what people were doing. This got started. It was my PhD advisor, Paul Braun, who I had actually helped with some fundraising in the past, who asked me to help him come commercialize this technology. And, it was really important to us to do something that initially I wanted to do a nanotechnology company. I was looking for something to exit my government service and really make an impact outside. And as he started this work, they were getting some really incredible properties on the battery. So incredible that it was kind of hard to believe. And so I really didn't want to be involved in trying to convince someone that we could do something we haven't demonstrated yet. So we were very fortunate that when we first started fundraising, we got funded pretty well, pretty quickly. And we really just wanted to kind of sit back, finish our fundamental engineering, really be able to make a good battery. And so when I would tell people the properties, and they say, wait, I don't think that's true, that's not right, then I could say, don't believe me, just test it and hand them the battery. And so it was really kind of an anti-hype. I'm from Texas originally. The companies in the Midwest were very much of the vein of, under promise and over deliver. And we knew up front that with a completely new technology to reimagine how to manufacture batteries, that it was going to take a long time. So we wanted to stay lean, really do our fundamental engineering first, and then get out. And with the pressure that comes with announcements and companies wanting to see things, that was when things really would take off. So we just wanted to do our homework before we took the test, basically.
That's really refreshing and, to be honest, rare in the hype cycle world that we live in. So it's great to hear that you took that diligent, patient approach. And so now I'm curious, what are those metrics that matter? The ones that you were saying people didn't believe you until they tested them. What are the ones that really matter for your application, and how much better can this technology be?
So, we started out, it was the world's highest power battery, and we actually had good power and good energy. And I know when you say power and energy to a lot of people, those sound like the same thing, but the total energy in a battery is how much electricity it can store. Power is how fast can you get that out, so a high power applications, a lot of amps real fast, a car accelerating hard, a really big drill that's under load. And then how much energy it has is how long can it last. And there's always a fundamental trade-off. When you really are under high load, it doesn't last as long. Back in the day, you would see that in camera flashes. where a really good camera flash that was really bright would eat a battery real fast. So that combination was really what we started with, was very high power and fast charge. Those were the really important things that we did. As we started commercializing, high power is much more of a niche application. And as we started dealing with people like electronics companies and EV companies, are like, yeah, the high power and fast charge is really nice, but we're moving from hybrids to EVs. Power, where you're converting from all of a gas engine instantly to an electric motor, that's high power because it's a fast transition. But in an EV, where you're really concerned about how far you can drive, that's a high energy application. So they said it would really be nice if you could do high energy and fast charge. And so we pivoted to that, and then along the way found the other things that were really important, which were, really good safety, that we had very high energy, but we also had really good power at that energy, which is very hard to do. And then safety, and then based on electroplating, which is a refinement technique, in addition to being able to create and deposit the materials, it could refine them at the same time. So we could start with low purity materials, which is really what that gets down to is low cost.
Hmm. Great. So when you say high energy, does that mean energy density? What's your
Yeah.
metric, your sort of figure of merit?
Yeah, so it's there's two ways you can look at high energy density. One is by weight and one is by volume. And so, and we actually have both. So in a battery of the same weight, we can double or triple the energy density. Very similar to how other advanced battery companies are doing that. We're kind of in line with the ones that are at the highest levels. And the same thing by volume. We can put more electricity in the same.
Basically started with some pretty broad marketing brushstrokes. It kind of a lot of really nice to have features. In your introduction, you mentioned nanotechnology. We're starting to get some of the specifics of the energy capabilities. What are some of the innovations that are changing? I think you mentioned one. You said something about plating and materials. What are some of the innovations you're focused on that are going to be disruptive here?
So we have two core technologies, both of which are about electroplating. One, what we started with was this nanostructured foam, which was created with electroplating. And so this nano sponge, if you will, is what we use as the basis for an electrode. Without getting into a lot of details on nanotechnology, what that usually means is very high surface area, and high surface area means you can keep the thin film aspects that give you the high power, and then kind of wrap that up into 3 dimensions, and then get enough of that thin film that you have a high amount of volumetric energy storage. And so it kind of breaks the trade-off, a physics trade-off between the ability to discharge fast and store more energy, because as you actually want to store more energy, you have to have more material in there, and then it takes the electrons and the lithium ions longer to go through that material. That's why there's a fundamental trade-off there. And then the second core technology, which really is probably the more transformative of the two, was the ability to just directly electroplate these cathode materials. So in the electronic space, you'll hear about cobalt-based materials. In the automotive space, it's either for high performance, it's nickel-based materials, and for less expensive cars, it's iron phosphate-based materials. And all of these materials are created as they're all ceramics, by the way. So they create this ceramic, which means they have a high energy firing process to convert it into this. Then they crush it, make it into powder. They put that powder in a polymer binder, which is very similar to paint, which is not conductive. And so then they have to dump in a bunch of carbon nanoparticles, usually carbon black, which is the same stuff that make your tires black, to make it more conductive. And then they spread that out on a piece of foil, aluminum foil, to actually make a battery electrode. And so we're skipping all of those steps. And so what we're actually able to do with the electroplating process is we run the aluminum foil into our plating bath. And so we're simultaneously refining, synthesizing, and depositing the final battery electrode in one step. And so we're taking 14 steps and putting them down into one step, and with the water-based rinse step. So we're getting rid of all the organic solvents. We're getting rid of all the capex needed to do those other steps. We're skipping 3 very highly energetic steps in battery manufacturing, which equates to both lower cost, but also equates to a much lower carbon footprint for lithium-ion battery manufacturing. So, and then we can actually use a broader range of starting materials in the electroplating bath because of the refining aspects of it. And so it actually helps North American supply to be able to skip the refinement steps that need to do, which are happening predominantly in China now.
Wow, that sounds like a lot and very sophisticated. Also, it sounds like because of that, you can be chemistry agnostic. Did I hear that? Where this manufacturing technique can be used across LFP or NCO or the different chemistries you
Yeah,
mentioned.
and so I would call it versatile, but not agnostic, because you do have to be able to electroplate those materials. We started out demonstrating it for manganese materials, which are still very relevant in the automotive space right now, and then moved to the cobalt-based material because we were really working first on wearables for electronics, and 100% electronic space uses this cobalt-based material. And then we've demonstrated the nickel-based materials and then the cobalt-free based materials. So what we're really trying to do is both match the material and our economies of scale in terms of our manufacturing capacity to market size. So I have a military background. Like I said, I joined this and started the company from the military. So we're starting out first with military and wearable electronics, then moving into the commercial drone space in terms of vertical takeoff and landing for like electric air taxis, and then moving into EVs. And then later on, we've identified the correct plating pathways for the iron phosphate based materials, but haven't actually demonstrated those yet, but feel confident that we can, so that we move later as that the stationary grid storage really continues to take off and become a larger part of the market. Then we're going to address that as we grow beyond our capacity to supply in the electric vehicle space. So it is very versatile.
Yeah, I wanted to ask about that in terms of volume. It sounds like a very logical approach in terms of selling to the highest dollar value applications per unit of production. So, where are you today in terms of volume, and where do you expect that to ramp over the next 5 years as you go into these different, you know, higher megawatts of deployed application?
Yeah, so our core technology is being able to make an electrode, which they make as rolls. And so we are currently at the pilot scale, so we can make small rolls of electrodes. We're actually in the final stages of building our production prototype line. And at the conclusion of that line, then we go directly into also, we've purchased a low rate production assembly system, and that'll give us the ability to do about 8 MWh of batteries. Next year, we're starting construction on our full production plant, which will be a 5 GWh electrode capacity plant. We have a second plant planned that will start about 18 months after that in Florida, which will go up to an initial 10 GWh, expandable into 20. So we're going to move from some of these smaller markets into the size that you'd see in the first plant in the major EV space, with plans to then expand later into Asia and Europe as well. So that we're doing this so that we can actually have impact. That's the whole purpose behind the company. And you can't have that if you can't scale rapidly. So we kind of waited and stayed in a low growth mode until we had the technology ready. And everything that we're doing in the electroplating mode, we can do out of basically the same electroplating roll to roll module. And so everything that we're doing is modular. So we can do, a different material. We can do the cobalt material or the nickel based material in the same bath. We just change the fluid, change the recipe a little bit. And then when we need to make more of it, we can just concatenate more modules to make the throughput higher. And so we feel like, and this production prototype is the first one with this modular based system, which is already designed. So we feel like we can rapidly scale that. So our plans are aggressive. I call what we're doing pragmatic boldness. We've got a bold vision, which is we're going to have 50 gigawatt hours of capacity by 2032, but you have to have pragmatic steps. And so this basically cellular manufacturing paradigm where we're replicating this one machine, just replicate the hell out of that. And then that can do all the things that we're talking about, whether it be making battery powder, which is, by the way, just coating an electrode, scraping it off, crushing it into powder. It's then is kind of throwing away some of our technology, but then that actually helps us match up with the maturity level of the battery implementation at different companies in different industries. And so I believe that flexibility is the key to implementation. So we really want to make what they need at the time that they need it. So if they are just looking for a source for powder, we think ours is better. It also has a single crystal nature, which was a similar basis to what Tesla had done with the million-mile battery. So we think that there's some technology advantages to what we can do there as well. But then as they get used to that and then they start to plan new products, they can implement our electrodes into their current assembly lines. And then later on, farther out in the cycle, they can actually use our complete cell, which is the highest advantage they could get to. So what we're really trying to do is enhance the flexibility to get it into as many products as possible so that, we can have that impact.
Now, that's a pretty aggressive growth plan. I think, going to 50 gigawatts or, it seems like a pretty rapid growth plan. How much of this comes from your background? So you started, I think in our pre-call, we talked about your Bell Lab days and the nanotechnology and your military experience. This start is something kind of as a security type effort? Is this a DoD initiative initially, or did you start this independently from that? Or are we taking a military application and putting it into civilian life?
I really saw the potential of nanotechnology from the military perspective, but I really wanted, and I definitely want to be able to give the soldiers the best products they have right now. One of the things that we're trying to do with this is put it into a pack that a soldier wears. It actually goes. It's a pack that's flexible that goes behind the armor plate in a bulletproof vest to run his night vision goggles and his radios and things like that. But this is really driven primarily on the commercial side. I mean, military is something that's very near and dear to me, but I really want to make an impact. And so it has to move beyond small applications into large applications. So, and then, we're in essence a spin out of the University of Illinois. That original technology we licensed from the University of Illinois. Paul Braun is the professor there who invented that nanostructured foam. And then the company took that, then later developed the ability to directly electroplate these cathode materials, which is the second part that we're doing there. So, yeah, we're really very much driven by commercial technologies, although we're helping where we can with the military.
That makes sense. I guess the other thing that kind of was a head scratcher when we first spoke is Ohio, Dayton, Ohio. I think your first plant's Ohio. Um, what makes that uniquely qualified as a good starting place for your venture?
Well, that's a really good question. When I started the company in Dayton, which is where I live, is where the Wright-Patterson Air Force Base is and the headquarters of the Air Force Research Labs. But then in order to get the license from the university, they require us to be in their incubator for a year. So we actually set the company up in Illinois in the Midwest. And then as we were getting ready to exit the incubator, we looked pretty broadly about where we wanted to be. And so one of the things that I did was I put an old elementary school map up on a wall, and I drew a 250 mile radius around all the locations that we were looking at. And then I mapped battery suppliers and I mapped major research universities. And the Midwest has a battery corridor. There's been traditionally batteries in Indianapolis, in the Chicago up into the Milwaukee area, a bunch in the area around Detroit. And then if you look at the number of research universities that were within that radius, the only place that came close was Boston. So the Midwest has more in that area than the Silicon Valley, than the Research Triangle, in North Carolina, then the area centered in Colorado around, the Boulder, Denver area. And so it made a lot of sense. And we wanted to manufacture, and the manufacturing breadbasket is the Midwest. And I'm also a little bit of a contrarian, and I really wanted to bring high technology back to where all this started. We're in Dayton, Ohio. Dayton was actually the Silicon Valley of the United States until about the 50s and 60s. I mean, there are actually still more inventions per capita in Dayton than there are anywhere else in the world. I mean, you had the Wright brothers, you had the start of a lot of the General Motors. The parts division was AC Delco, which I'm probably butchering this a little bit, but it was basically the Dayton Electronic Lab Company. So there was a lot of GM origins in Dayton, a lot of interesting things. And I really had a passion to make sure that the manufacturing came back, and that domestically, and that everything that we were doing doesn't have to be on the coast. It can be spread out across the United States. I think the coasts are saturated with entrepreneurship, and I wanted to bring that entrepreneurial aspect and kind of regenerate it in the Midwest.
Mhm. That probably helps as well with domestic content post IRA. So you also mentioned some supply chain innovations where the refining step maybe wasn't necessary and could be done domestically as well. So when you think about those supply chain factors as it relates to upcoming incentives, are there advantages as well?
Yeah, there certainly are. So one of the things that we started out with, we actually we modeled our electroplating process after aluminum refinement, which is the Hall-Héroult process. So it's molten salt electroplating is how they refine aluminum. So we knew starting out when we started this low temperature molten salt electroplating process, which is what we use to make these cathode materials, that we could use lower purity materials. And we started out demonstrating that we can move from battery grade, which is like 99.9% pure, down to technical grade, which is somewhere around 80% pure. And even just that jump from 99.9 to 80 can create about a 35% cost reduction in a battery. And then we actually wondered, okay, we know we can go this far. How far can we go down? And so as we finished our first generation of product and actually started going out looking for raw materials at the mines, we were in Western Australia, and somebody said, well, hey, why are you using this lithium hydroxide based material, which for the listener is, one of the prevalent full highly refined materials that they use in the commercial lithium batteries today. It's the most prevalent lithium precursor. And they said, well, why don't you go to this, another random thing, sulfate materials? And I said, well, we've done that, but I don't know how far we can go down the purity chain. And, then when we demonstrated it, he got really excited about it. As a matter of fact, he stood up, reached across the table, shook my hand, said, I've been waiting 30 years for somebody to do this. And I was like, wow, I really have to go back and understand the refinement chain for lithium. And that's when I realized that this 80% lithium sulfate was the input to the lithium refinement plant. And so by going from one material to a lower purity, different material, I had skipped a plant, and I'd already skipped a plant by not having to make battery powders. And so if you think about it, we had skipped two complete multi-billion-dollar refinement plants at scale. We'd skipped all the labor, all the equipment costs out of those, but more importantly, we'd skipped two super high energy steps in making a battery, which also helped us lower the carbon footprint. And so we knew that we had a large carbon footprint reduction, but we didn't really know how to quantify it. So we worked with a company in London called Minviro to do an initial life cycle analysis in terms of carbon footprint. And just by using that one lower quality, lower purity lithium material, it reduced the end-to-end carbon manufacturing footprint of lithium-ion batteries by 20 to 40%. And now we've demonstrated that we can do that with low purity nickel and low purity cobalt. So it's a dramatic carbon footprint savings, but it's also a dramatic cost savings. And then it gets a little more subtle, but it's just as important. What we've actually been able to do is, cobalt and nickel are not, the natural abundance is not the problem with these materials. It's actually finding it in the ground in a point that there's some vein that's high enough purity that they can get it out of the ground and make money and not go out of business. And so the fact that we can use these incredibly low purity materials means that we can make that economic. So there are mines all over the United States that have been closed because they weren't economic to extract. So we can help them open new mines. There are some that are already opening, and they're just about to start getting raw materials out of the ground, but they have to send all those materials to China to get them refined and then bring them back. And so the fact that we can use them without refinement as they are coming out of the mine means that, you know, that material can be accessed 2 to 4 years early. And so we've increased, hopefully worldwide, the amount of battery materials that will be available and made it where it's a lower carbon footprint to do so. So that's the piece that I think could be the most dramatic of anything that we're doing. When the battery space, you know, a few years ago really started to grow as EVs took off, everybody's like, I need the highest performing battery. And now they're saying, I need a battery because there's shortages in raw materials. And so it's really moved from where is the edge of the technology to what can I practically manufacture and how can I get the raw materials. And so for us to compete domestically in that, we have to grow holistically the whole supply chain. And the fact that we can sell to other battery manufacturers, we can make higher performing components, we can make a higher performing battery, but we can also give them access early to these refined materials. You know, I mentioned cobalt, nickel, and then on the lithium side, the hard rock lithium, which comes out of a granite bearing mineral called spodumene, which is in like North Carolina and in Quebec. And that's also what all the stuff in Australia is. You know, we could use those in that process. But we also recently just demonstrated that we can take our battery electrode, which we spent a long time doing. Xerion has, to my knowledge, the first practical, fully dense solid state cathode. And that whole design, which took 8 years to develop, was to efficiently move lithium in and out. And the fact that it's fully dense means water or other solvents don't go through it. And we're like, holy cow, our electrode would make a great separator membrane for the Salton Sea and other lithium brines. And so we entered into the Department of Energy's Grand Challenge on direct lithium extraction and won the DLE Lithium Prize about a month ago after a 2 year and 50 teams. And so we've also created a system that can take these low purity lithium chlorides with high selectivity and go directly to the final battery material for others, or move it directly into our molten salt bath for our own use. So it's really a pretty broad-based way of accelerating the supply chain, which right now in the battery space, I think is the most important thing we have, especially domestically, and then later on for the whole world.
Wow, that was quite a bit of information, and it sounds like you guys are doing quite a lot. I guess the one thing, as you're describing all this technology and process that was going through my mind is, I tend to be in the software space a lot of the time, so we can quickly come to market with and scale ideas. But when you start going to physical things like manufacturing, you have a supply chain of your own to do all this.
Yeah.
So if you're going to hit your goals, so I think you had Ohio plant is 2024, and then you had, future couple other plants that you were talking about. Is there a supply chain, or do you need specialized equipment to do your technique? And does it need to be built from the ground up, or is that what you've been doing over the last 8 to 10 years, kind of building that material?
It's exactly that modular electroplating system that I was talking about. So it can do all of that refining aspects as well, except for that lithium brine piece, which is just our electrode, which is what we've built. So all of the things that we were talking about in terms of nickel and cobalt and other materials, and being able to kind of actually do some of the refinement aspects of those is using our process. The brine selection, lithium extraction, is actually taking our process to make an electrode and then using that in a specialized application. So it's all coming out of the same machine. And we already have the design for that machine. Like I said, we've already built the initial production prototype of that machine. And so now it's just replicating that machine and using it across all these different varied things. So people hear a lot of what we can do and they're like, wow, these guys must lack focus, because they're all over the place, but it's all coming out of the same machine, just different applications.
Mm-hmm. So coming back to the consumer impact, because you mentioned that was a major motivator for you. So let's talk about success and what that looks like. Ultimately, you're selling to another battery manufacturer. You're either selling the powder or the machines, and then what are they able to build with that? So think about an EV. Is that a instead of going 300 miles, it can go 400 miles?
Yeah.
So who are you selling to, and what does that impact?
So all the people we're working with, and we have joint development agreements across many people in the electronic space, in the drone space, and in the electric vehicle space. We're giving them security of supply so they can get the same thing that they're doing now, and they are ensured that there's the raw materials to keep getting that. They can get the domestic content, which is recently was just what we've always been working on, just from a qualitative perspective, but from the IRA things has all of a sudden become a real pressing problem in terms of how do you keep the tax credits that you have for EVs, and that's really actually kind of helped our demand in our business side. And so that's what we're providing early. And then as they adopt the electrodes, like I said, we have the highest energy that you can make, just like some of the other advanced battery companies. You're kind of getting to the point where, based on a particular material, you've gotten the most efficient packing you can inside the battery. So they're all going to kind of plateau at the same spot. But we're there with them, and when those come in, we have a battery that can do the same thing, that's less expensive, much less expensive, and safe and fast charge. And so, we have all the compelling pieces on the end user side, but companies want to adopt it because we can use a wider area of material, which means we have better secure supply, and we're doing it domestically. And so we're really kind of vertically integrating, and the only company right now in the United States in the battery space that's really kind of done that is Tesla. So, and they're the ones that's been really successful because they went back and they secured that supply. And so, we were doing this before Tesla got popular, but it is kind of in the same vein.
Great. John, this is really fascinating. We've touched on consumer applications, the manufacturing process, the upstream supply, and how it all fits together. How did you get to a point where you feel comfortable? I mean, you've kind of gone in and out of all these topics. So can you tell us a little bit more about your background and the things that you've done before Xerion that you feel most prepared you for what you're doing now?
So, my entire background prior to this was in the U.S. military, and so I started out. I graduated with an aerospace engineering degree from Texas A&M. I came into the Air Force as a military officer right after the first Gulf War. And they said, "Well, what do you want? Where do you want to go, and what do you want to do?" And I knew at the time what I wanted to do. I said, "Well, I want to go to Wright-Patterson Air Force Base in Dayton, and I want to do materials." And they said, "Great. Well, we're sending you to Wright-Pat, and we're going to make you a financial manager because we've got 140% of the engineers that we need." And so I spent my first 3.5 years in finance, first as a financial manager, and then they sent me back to school and trained me as a cost analyst. So I was doing cost estimates across a range of things, anywhere from R&D to logistics. And that, I think, was the first thing that really prepared me well, because even though as an engineer, it's not what I wanted to do. It was something that I found was very beneficial in the company. And then my research group in the Air Force Research Labs was in the materials. They're divided into directorates. I worked in the materials directorate and specifically in the manufacturing technology division. My dad was a manufacturing engineer for 40 years. I've always been very passionate about that. And we were set up as a materials scale-up group in that group, doing the research that we needed to do in order to automate and increase the yield of new materials and materials technologies. And so we were doing that with neural networks and genetic algorithms and data mining in the mid 90s. So we were doing AI based materials research when it really was not popular. As a matter of fact, people were very skeptical of that. But what that did was we wound up touching a broad number of technologies and material systems. And so I really became a generalist when it came to understanding where different materials could be impacted. And then later on, I went back to the Air Force sent me back to do my PhD at the University of Illinois, Urbana-Champaign. And I did that. I had that interest in nanotechnology, and it was my entire focus was how can I manufacture a nanotechnology practical? So assembling nanoparticles, manufacturing techniques. And with all that hype in the nanotechnology space, just like the battery space now, It was, I want to find the real things and make them practical to manufacture, because that would lead to the impact. So all of my desire for impact grew out of that nanotechnology space, and honestly has nothing to do with batteries today. Batteries were the first instantation where I saw that I could really have a dramatic impact. So it's really been about the impact, not about the batteries themselves. That was just the first area that we chose to try to impact.
Well, you had an amazing journey to get there. I guess the question I would have is, if I were a younger person just starting my career journey today, listening to this podcast and excited about the battery tech and where electrification is going, what advice do you have to someone just getting started here?
So, I stayed in the reserves so I spent 7 years active duty in the military, and then got out, stayed as a government civilian in the same job, but then became a reservist. And so, as a senior military officer, I would give young lieutenants coming in advice. And, the advice that people would typically get is, oh, you got to do one tour in the Pentagon. You got to make sure you have a joint assignment. So make sure you work with the Army or Navy or something like that. And they had this very prescribed way to success. And my advice was always, forget all that. There's only 3 things you need to do. I said, find what you love, do it with all your heart, and the rest will take care of itself. And so I've always been really passionate. It's science and technology for me. I'm super passionate about it. We got a real problem with it in the United States, and it's embroiled in our educational system. People don't want to go into that anymore. So I've always thought, as a retirement job, I'd go teach like high school physics or something like that. But I'm going to come in my $1,000 suit driving a Porsche and say, yeah, science did this. Forget the green slime that you make to get kids interested in science. I want them to see, if they apply themselves and they can effectively articulate what they're doing and then have a dream, that they can get to those end goals that they traditionally want to do, which is have success and be able to take care of their families.
Wonderful, John. It's a compelling vision. We're looking forward to that date when you roll in your 500-mile EV
That's right.
and enabled it via what you're doing here today. This was really eye-opening. It's a part of the battery supply chain that I don't normally think about. I didn't really know anything about coming into this conversation. So this has been really, really helpful. Thank you so much for taking the time with us today.
Thanks. Pleasure to do that. And obviously I get excited about what we're doing and trying to make sure that the whole industry gets to where we need to do to really impact and hit the change that we all need.
Well, thank you, John. That's been an amazing conversation for our audience. We hope you've enjoyed this conversation as much as we did making it. It was eye-opening, as Jeff said. We learned a lot about technology. There's a lot of bold changes coming here. If you can reduce the demand in the supply chain and reduce the steps, hopefully we make a better impact for the environment and we see this technology take off. We look forward to checking back with John in the future to see how his vision comes to reality. He made a bunch of bold predictions, so I'm looking forward to touching base in a year or two to see where his company is again. If you've enjoyed the content, don't forget to subscribe, follow us so you don't miss that follow-up interview in the future. And we'll see you again next time on the Insider's Guide to Energy podcast. Bye-bye for now.